Right now, across global finance, judicial systems, and autonomous networks, automated algorithms are making decisions at a scale and velocity that human beings cannot physically monitor. Millions of choices are executed in the blink of an eye. This speed relies on a foundational architecture that has powered computing for decades, the binary gate. Everything is a 1 or a 0, proceed or halt. But when a modern AI system encounters genuine moral uncertainty or lacks clear data, this binary structure forces them into a guess. They cannot hesitate. We call this binary brittleness. To maintain computational throughput, the system hallucinates certainty where none exists, executing flawed, highly consequential decisions at mass scale. Because these systems prioritize speed over verifiable certainty, they create a permanent shield for the institutions that deploy them. When an algorithmic failure causes real-world harm, the speed and complexity of the binary decision provide built-in plausible deniability for the human operators. The engineer who saw a way to fix this structural defect is Lev Goukassian. He isn't a historical figure from the early days of computing. He is actively designing solutions today. But Lev is building under a severe constraint. He is living with advanced cancer and operating on a finite timeline of roughly 6 months. Faced with a terminal diagnosis, most people might rush to publish or finalize their remaining projects. Lev did the opposite. He deliberately slowed down to question the very first principles of artificial intelligence. It is a striking irony. A man with almost no time left to live has dedicated his final days to creating a structural, physical pause button for artificial intelligence. Knowing he will not be here to oversee the arrival of artificial general intelligence, he realized his framework had to survive without him. It had to be driven by rigorous responsibility and permanent architecture, not ego or personal recognition. Working from a sunlit environment, Lev actively collaborates with AI tools themselves, running iterations, breaking models, and rebuilding them to test his governance theories. He realized software or legislation will eventually be bypassed by a capable AGI. Governance must be baked directly into physical hardware. His solution, Ternary Moral Logic, introduces a third physical state to computation without dismantling the high-speed binary systems we currently rely on. He calls this the dual-lane architecture. The AI's binary inference engine, Lane 1, continues to process patterns and generate tokens at maximum speed. Meanwhile, a completely separate parallel ternary lane, Lane 2, handles oversight. This division is essential. The binary system proposes an action, but a sovereign physical coprocessor reviews it. Governance cannot be left to the interpretation of the AI's own neural network. It must be enforced by a separate physical gate separating intention from consequence. The core of this ternary lane is a mandatory third state called the sacred zero. Triggered by moral uncertainty, it drops the voltage to a stable intermediate state. At that moment, it becomes physically impossible for the machine to execute. The computation stops. This pause is governed by a strict architectural rule. No log equals no action. Before proceeding, the AI must generate a moral trace log. This permanent, immutable ledger forces the system to document its exact reasoning, risk assessment, and specific mandate evaluations. This record functions as a cryptographic lock. The physical actuator that carries out the AI's decision cannot function without the decryption key generated by a successful, transparent log. If the logging fails, the action is physically blocked. By tying execution to this log, TML moves ethical hesitation to a hardware constraint. The machine stops because the circuit itself no longer carries the current needed to proceed. The AI earns its right to act by leaving an honest trace. This architecture scales far beyond the laboratory. By embedding these chips in the servers governing the execution of software in healthcare, banking, and government offices, we create a hard floor for institutional behavior. If the coprocessor doesn't authorize the voltage, the bank transfer doesn't execute, and the judicial order isn't filed. Over the next 50 years, trillion-parameter models will become too fast and too complex for traditional human oversight. Without a physical mechanism that forces them to pause and explain themselves, we risk building a world we can no longer govern. The ultimate legacy of this system is its permanent evidentiary record. By requiring machines to document their reasoning, future generations will be able to audit and learn from technological failures, rather than suffering through them blindly. We have spent decades optimizing systems for speed. The architecture of ethics must now be treated with the exact same rigorous engineering standards as the architecture of computation itself. This leaves us with what Lev calls the burden of knowing. He has proven that hard-coding accountability into AI is technologically possible. Because the blueprint exists, society can no longer plead ignorance. Whether Lev's specific hardware substrate is universally adopted, or whether we build on top of his theories, the moral imperative is clear. We now know how to require a pause, and we know how to demand a trace. As an architect, Lev's framework is complete. His final act is passing the baton, offering this blueprint to the engineers and policymakers who will outlive him. Lev's final thesis is a call to action. The technical framework for accountable systems exists. Whether we use it to build a safer future depends on the choices made by the people who implement it.